All right, good evening, everybody. I appreciate you joining us for this Weather Ready Nation FLYERS webinar on icing. This is a collaboration project between the Aviation Weather Center, the Kansas City Central Weather Service Unit located in the Air Traffic Control Facility, and the Kansas City Weather Forecast Office. So I want to acknowledge and give credit to Chelsea Kenyon from the Aviation Central Weather Service Unit, Nicole Starzek, Kevin Sullivan, Scott Minnick, Brandon Burton from the Aviation Weather Center, and then I'm Brad Tiemeyer, and I'm coming from the Kansas City Weather Forecast Office. So I'll be talking a little bit about some of the main focuses of aviation icing, and then Chelsea will give you some examples of what that has resulted in the field, and finally Nicole will go through a preliminary or show you how to access some of the features on the AWC website. All right, so why do we care about icing? Icing is mainly formed through two ingredients: visible moisture due to clouds and freezing temperatures. And icing is defined as any deposit of ice on the aircraft, and is basically supercooled. And what supercooled means is that the temperature is below freezing of the water droplets itself. In the atmosphere, water, there's a lack of ice condensation nuclei, and so because of that, water can become supercooled. And we'll talk a little bit more about that. But icing occurs most often in the winter and spring months. In the higher latitudes in the spring and the fall, and in the winter months it's too cold up in the high latitudes to really get ice to form, and that's when your icing threat moves further south towards the mid latitudes, and that's why we see the most frequent icing threat in the fall, winter, and spring months here in the mid latitudes. And that shift in the icing threat in the tropics is mainly focused in the winter months because the atmosphere is generally too warm to sustain ice throughout the rest of the time of the year. But like I mentioned, the icing threat is mainly due to supercooled water droplets, and we'll talk more about where those occur in the atmosphere. It's not actually caused by ice itself. If ice already exists in the atmosphere, that ice is not going to attach itself to the aircraft and become an issue. So that's why flying in very, very cold environments is actually good for aircraft, not only for giving you lift, but also the threat for icing is fairly minimal. So the impact, the dependent icing is most focused on, or is most dependent on aircraft size. So the duration of exposure to the ice, the wing orientation can impact the amount of ice that we see across an aircraft. Here's some examples on what icing looks like, and it's a cumulative effect, meaning the longer an aircraft sits in an air mass that's producing ice, the worse the hazard becomes. Icing on an aircraft increases the aircraft weight and reduces the aerodynamics of the aircraft itself. So here's what I mean by the cumulative effects of icing. So what that means is that it increases the weight of the aircraft itself as you continue to add ice to the aircraft. It increases the amount of drag that the aircraft experiences going through an air mass. It also decreases the amount of lift as you're not getting efficient airflow across the wings. And then finally, it decreases the thrust and pulls down the area. Gravity pulls the aircraft down towards the surface, decreasing the thrust and slowing your momentum through that area of icing in the atmosphere. So like I talked about, what you're really looking for is supercooled water in the atmosphere, and that forms in the atmosphere generally just below 0 Celsius all the way up to as high as -40, and there doesn't have to be a warm layer in the atmosphere for supercooled water to form. So it's generally in that atmosphere that's below freezing, and water is cooled rapidly through lifting processes, which is what results in that supercooled water. And because of in the atmosphere you have a lack of ice condensation nuclei, water doesn't automatically freeze once it gets below freezing. So because of that, you're looking for supercooled water in the atmosphere, and that will readily exist anytime you have visible moisture in the atmosphere, and it will start to freeze more on contact once you get above about -8 Celsius. So in that 0 to -8 layer, that's when you're really going to start to see the potential for icing when you have visible moisture present in the atmosphere. So icing factors can really vary across the area due to liquid water content in the clouds itself, the temperature of the atmosphere, the droplet size, and the cloud types. Supercooled water droplets often exist in stratiform and cumulus clouds both, and we'll talk more about that here in a bit. When supercooled water comes in contact with the outer surfaces of an aircraft, the amount of icing depends on a variety of several factors, including the residence time of supercooled water droplets, the airspeed, and the geometry of the surface in contact with the supercooled water droplets. So clouds in the environment are colder than the freezing level, have to be present for long periods of time, will have relatively little supercooled water as the ice nuclei will attract supercooled water vapor, changing the phase to ice. So initially, a relatively newer cloud is going to have more supercooled water potential than ice potential. The temperature ranges of -5 to -12 have the highest supercooled water liquid content, as seen here in this image. That's where you see the greatest supercooled water, and temperatures below that, the supercooled water will start to freeze in the atmosphere, and that's going to be where you see the most significant potential for ice, is in that layer, especially when you have that visible water layer in the atmosphere. Here's another graphic that shows where most ice tends to occur, and most ice generally occurs below 22 Celsius. So once you can see here, once you get below that temperature range, most water at that temperature range is going to be in the ice form itself. So if you get above -22 Celsius, so in the higher portions of the atmosphere or in the colder portions of the atmosphere, that's when you're going to see the most ice that's available in the atmosphere, and that's not going to impact aircraft itself. One thing to be really cognizant of is if you're spending significant amounts of time at altitude and then you drop back down into a warmer air mass, your freezing potential still exists even when your aircraft is above freezing, and that's because your aircraft skin temperature remains very cold. And so if you have visible water content, even just slightly above freezing, that can result in significant amounts of icing on the aircraft itself. So like I mentioned, most icing is generally concentrated in those air mass just below freezing, 0 to -15 Celsius, but you can have icing as cold as -40 if those lack of ice condensation nuclei are not present. So here's how ice starts to form on the wings of the aircraft itself. It's related to the droplet size and how it forms, because there's two different types of icing. One's rime icing and the other is clear ice, and we'll talk a little bit more about that here in a second. But water droplets initially impact the leading edge of the wing and then start to build up mostly on the smallest radius, and that's just the way, because that's the way that surface is more exposed than other surfaces that might be on different parts of the aircraft. So that's where you start to see ice build up, is on that initial part of the wing, leading edge of the wing where the radius is smallest, and then you will continue to see that ice continue to grow with time. So like I mentioned, it forms on the surface, the smallest radius of curvature on the leading edge of the wing, so that's where you start to see that, and then it will build and increase in scope over time. And really, the amount of duration and exposure that you have really can impact the potential for icing itself on an aircraft. So like I mentioned, there's three different types of icing: clear ice, rime ice, and then a mixed combination of both clear and rime ice. There is also induction icing, which can impact carburetors on aircraft, but in this particular case, we're not going to talk about that in this talk. So rime icing is generally opaque or milky in color and is relatively translucent, so it's hard to see through. And the reason why is because it's associated with small drops in the atmosphere, and those small drops, when they instantaneously freeze on the aircraft surface itself. And when they freeze, they trap air in the ice itself, which leads to the opaque or milky appearance of it itself. Clear ice, on the other hand, takes a little bit longer to freeze, and it's typically made out of larger drops. So larger drops hit the surface of the wing, spread out over time, so they spread out across the wing, and as that drop spreads out before it freezes, it releases that air. So given that that's the case, you get clear ice, or ice that you would see that you can easily see through. And that forms generally at temperatures around 36 to 14 Fahrenheit. It is the most dangerous type of ice, however, though, because it's relatively heavy and cannot be easily knocked off by anti-icing equipment. Mixed ice is a combination of rime ice and clear ice itself. It generally forms at colder temperatures, 14 to 5 degrees Fahrenheit, or -10 to -15 Celsius, and can occur with different size drops. So you get those larger drops that leads to the clear ice, smaller drops leads to that rime ice formation on the aircraft itself. So like I mentioned with rime ice, you get smaller drops that impact the aircraft wing, that traps the air near the surface of the wing itself and leads to a frost-like or opaque appearance of the ice buildup on the leading edge of the wing. And that typically forms in that near freezing temperature, so just above freezing if the aircraft temperature is below freezing, and then to just below temperatures well below freezing to around -15 or -20 Celsius. So you tend to have rime icing that forms on the leading edge of the airfoil, and clear ice might actually make its way back a little bit further on the wing because of that process of being forced and remaining liquid longer on the wing before it freezes, in the process of releasing the air before it freezes itself. It's easier for the anti-icing equipment to remove rime icing, and rime icing is also a lot lighter in weight than clear ice itself. So let's talk a little bit about clouds and what you might see out there, and what the severity of icing is with clouds. So we'll talk about cumulus clouds, high clouds, and then stratiform clouds. Cumulus clouds are basically clouds that have a puffy appearance, and with the cumulus clouds you can have clear to mixed ice because you're dealing with typically with larger droplet sizes in cumulus clouds itself. If you're dealing with an actual thunderstorm, though, you can have some rime icing up towards the top of it, where you would have more smaller droplet sizes, and possibly ice crystals themselves, which would not be an icing hazard to the aircraft itself. But closer to the precipitation production layer inside the shower and thunderstorm activity itself, that's where you're going to have your larger droplet sizes, and that's going to lead to more clear icing. Obviously, thunderstorms, aircraft like to fly around thunderstorms, but even around showers and thunderstorms itself, you can still get light precipitation that could lead to the potential for icing. With stratiform clouds are tricky in the fact that they generally have a large footprint across the area, and they can lead to significant amounts of icing. Generally, stratus clouds, though, are generally confined to a few thousand feet thick, so you can usually change your altitude to try to get out of the most significant areas of icing themselves, but realize that traveling aerial distances across the area may not allow for you to escape the hazard as easily as changing your altitude themselves. High clouds are generally formed out of ice crystals themselves, so given that they're already in the form of ice, they don't have a high threat for significant icing to aircraft themselves. Finally, I want to talk a little bit about freezing precipitation. So sometimes in the atmosphere, we'll get a unique setup to where we'll have a warm layer in the atmosphere that's above freezing. So in the atmosphere, you start to get precipitation that develops as snow, but then it melts when it reaches this warm layer as it's falling towards the surface. And then in the near surface layer, you've got cold air that's trapped near the surface, and as a result, you can get potential significant amounts of ice, not only on the surface, but also on aircraft that are trapped in this cold layer near the surface. In these types of situations, the best thing to do is to change your altitude, but the best way to be advised of this is to get your weather briefing and be aware of the potential conditions that you might be exposed to in the first place. With that, I'd like to say know before you go. There's a lot of options for weather information out there. Get your pilot briefs, aviationweather.gov, and there's also several different places where you can get satellite information and get weather information. So know before you go and know your potential hazards and risks. Finally, I'd like to thank Sally Johnson, Janice Maldonado, for their work on putting together this presentation. And with that, I'll hand it over to Chelsea to talk more about what this looks like in the field.
So now let's talk about situational awareness, one of the things that pilots need the most in just about any situation, but especially when we're talking about icing. So we'll go over just a couple of things about icing, pilot reports for icing. I'll talk about a specific event that we had here in the Kansas City area, and then we'll talk about some takeaways. So again, winter is a hazardous time of year to fly. You have a lot of temperature changes, especially in the middle of the country. Air masses are clashing together. The jet stream is stronger. We have stronger high and low pressure systems and fronts, more winds, more clouds, more icing. So this is where all the ingredients tend to come together. Icing danger zone. So one of the areas that you want to watch out for is north of the warm front. That's where you get into the stratus clouds that Brad was talking about, and that warm nose that usually extends just a little bit north of the actual location of the warm front. So that's a kind of a prime area for some icing. Also near cold fronts, if you're very close to the front, you have that lift, and it can create cumulus clouds. That's where you start to get into your supercooled water drops, and you can accumulate icing there. Also moisture wrapping around the backside of the low pressure system. Usually you end up with some banding or some areas of precipitation there, and usually some cloud cover and icing as well. A couple of types of precip to watch out for. If you see these in a METAR or a TAF, freezing rain, freezing drizzle, PL, that's ice pellets or sleet, and then freezing fog. Any of those are going to should be setting off that little red flag that you could be looking at some icing. And also multiple freezing levels. If you see that in a briefing or on a map of freezing levels, watch out for that, because you're probably looking at an enhanced icing threat in that area. So to avoid ice in flight, just get out of the moisture. That's probably the quickest, fastest way to do it. Get out of the clouds, get out of the precipitation, find some clear air, and then you will be out of the icing. So find your VMC. You could change altitude. Sometimes icing layers are only a couple thousand feet thick, so if you can get above it or get below it, find those warmer temperatures, especially if you're in a multiple freezing level situation, you might be able to get yourself out of it as well. Find those colder temperatures. When you get close to -20, it's probably too cold for anything to stick to your aircraft at that point. So then you're going to be out of the icing as well. Look for negative icing reports. Give negative icing reports. If you're in the clouds and you're not getting icing, pass that on. That's really valuable information for the next pilot or the controller who might be working that airspace as well. A couple of different things I wanted to talk about here. This has come up when I've talked to pilots in recent days, and one of the techniques that I use when I'm forecasting icing, and sometimes we don't have all of the data available to us when we need it. Like early in the morning, I don't have a lot of pilot reports in the system. I need to know what's going on. Sometimes there's other ways you can get that information. One of them is called the VAD wind profile. This is kind of an old school way. The VAD wind profile has been around as long as our radars have, so since the late 80s. And the VAD wind profile actually picks up on scatterers in the atmosphere above the radar site, and it shows which way they're moving. So it's actually a vertical slice above the radar. And the way you read this is it will give you just like a vertical slice every couple minutes. And so the most recent time is going to be on the far right. So every couple minutes you're going to get a slice. Now sometimes if it's really windy, you may not be able to pick up the clouds, but on a good cold winter day, if you've got a cloud deck, it really does pick it up. So what you're looking at there is just thin clouds. Again, not a lot of scatterers, maybe just a little bit of ice. It's hard to kind of pick out. But if you look at a good thick cloud layer right over your radar site, this is what it would look like. So at the surface, you can see the winds are light, but then as you go up in height, they start to pick up a little bit. And you can really just generally pick out from about 2,000 feet to up around 10,000 feet. That's where this stratus layer was. And if you know the freezing level for that area, you can infer that icing is going to be occurring from the freezing level to the top of the cloud deck. So that's one way that you can kind of estimate. It's not going to work in every situation, but it actually does work pretty well in the wintertime. So that's one way you can do it. The other way, if you're pretty weather savvy, is you can use a SKU-T. And if you haven't learned how to look at these, it's a really valuable tool to use. So this is where you're looking at cloud layers. This is another vertical slice of the atmosphere. This is taken by balloons. And what this does, it shows you the red line is going to be your temperature profile, and the green line is going to be your moisture profile, your dew point. Where they come together are pretty close. You can expect the air mass to be saturated right there. That's your cloud layer. So in this case, the base is going to be down here, maybe around 3,000 feet. And then the top of your saturated layer is maybe 10 or 11,000 feet. So you can kind of estimate where the bases and tops of the cloud layer is going to be. And then it even gives you the 0 degree isotherm, the 0 degree line. Everything you see is colder than 0 degrees. So you can expect icing anywhere that you are getting saturation here, all the way down to about -20. So that is where you would be looking for icing. And sure enough, on this day, this is what we were looking at. This was over the St. Louis area just a couple of days ago. You can see all these icing reports that we were getting between about 5,000 and 10,000 feet right over that area. So it picked it up really, really nice. And that's just another technique that you can use. Maybe you're not comfortable with a lot of the products that are out there. That's one that is worth getting to know. It's useful even in the wintertime. It's not just for thunderstorms. So those are just a couple of ways that you can look at icing. But the best way to know is to get a weather briefing. And I am a big proponent of weather briefings, and pilots should absolutely check. And if you don't know what you're looking at, call a weather briefer. I know they're not as easy to get a hold of as they used to be, but get a weather briefing. It's super important. Check for updates. So if you get your briefing a couple hours before you go, check again right before you take off, because a lot of things can change. And look for the AirMet Zulu. That's your AirMet for icing. If it's over your area or even close by, you need to be looking for icing. SIGMETs or center weather advisories for icing mean that it's happening and it's affecting everybody, and it's probably pretty bad. I would definitely not fly in a SIGMET for icing. In your METARs and TAPs, again, look for those freezing precipitation types: freezing rain, freezing drizzle, sleet, freezing fog. even a rain-snow mix, if the temperature is close to 0, you could probably pick up some icing in that area. And then again, look for pilot reports. Give the information to get the information. So pass on when you're not getting it, pass on when you are, what the altitudes are. Remember to pass on the temperature outside when you are reporting icing. So again, when you're reporting icing, trace, light, moderate, and severe are the reportable types. Do not report heavy. That's not a thing. But if you're not required to use your de-icing or anti-icing equipment, it's probably just a trace. If you have to use it occasionally, maybe it's light. If you're continuously using it in order to stay safe, that's moderate icing. You probably want to think about getting out of those conditions. And then if you have to get out of it because you can't keep up with it anymore, that's severe. That's the urgent one. You don't need to be in there anymore. And we're going to talk a little bit more about severe icing here in a moment. Okay, so the FAA, air traffic controllers, actually have a requirement to solicit pilot reports from you. So 5 miles or lower visibility, 5,000-foot ceilings or lower, when you're deviating around thunderstorms, if you're in moderate or greater turbulence, light or greater icing, and wind shear. If any of those conditions are happening, they're supposed to be soliciting PIREPs from you. So don't be afraid to pass that on to the air traffic controller you're talking about or talking to if you are flying IFR somewhere. All right, I want to get into a case study here. This is a situation that occurred almost exactly 2 years ago now. We had a great big cloud deck sitting over the middle of the Kansas City airspace, including most of eastern Kansas, and we had a very well forecast icing conditions there. You can see we've got an air met for icing from the surface up to about 6,000 feet. And looking over here, you can see all of the PIREPs that we had that day for icing. Tons of reports. Well forecast. There is no way that anyone should have missed this. It was briefed all morning to the air traffic controllers. Every pilot should have had it in their briefing in the morning. And we had a ton of marginal VFR stratus, lots of icing PIREPs. Again, most of them were in that 2,000 to 5,000 foot range on this particular day. Well, we had a GA flight from Rocky Mountain Metro in the Denver area to Emporia, Kansas. It was called IFR, the Cessna 206. And right about 1:30 in the afternoon, they were attempting to land at Peoria. So on the next slide here, we're going to get into what it sounded like to air traffic control. So Scott, I'm going to let you play this. Hopefully you can hear me.
November 206, Victor Sierra Center.
Yeah, I'm just broken out of a cloud. I don't show that I'm on my right course for the RNAV, so I'm just needing a little assistance.
All right, November 206, Victor Sierra, push notice is canceled. Pilot maintain 4,000 and flight present heading.
Okay, flying present heading and climbing to 4,000. Although I am clear now of the clouds, but okay, I'm climbing to 4,000.
All right, November 206, Victor Sierra, the Emporia weather, wind estimated 3308, visibility 10, ceiling 1,500, overcast, temperatures -5 dew point -10, estimated 3053.
I'd like to say visual if I could right now, otherwise I have to climb through the ice.
Right, November 206, Victor Sierra, you have the Emporia airport in sight.
Negative.
All right, November 206, Victor Sierra, maintain 2,900, the MIA here is 2,900.
Maintain 2,900.
Okay, November 206, Victor Sierra, did you turn yourself off the approach?
I did not.
Okay, are you sure you know how to fly the approach? Because you're supposed to go direct Emeti and then Avad for the RNAV.
Yes, I turned in from Emeti, and you know, I'm just, right now I'm really needing some help.
All right, no, medevac 191 Whiskey Bravo, contact Kansas City on 126.7.
126.7, another 112.
All right, November 206, Victor Sierra, say your heading.
I'm heading at 340, I'm at 2,800 feet.
All right, November 206, Victor Sierra, maintain 2,900. Let me know when you level 2,900.
I'm at 2,900.
November 206, Victor Sierra, flighting 090.
090, I'm heading.
November 206, Victor Sierra, state that what you're requesting now at Emporia.
I would like vectors to 01 RNAV approach.
Okay, I can't back to you for that approach. Unfortunately, it's not depicted on my first 01. I can't back to you for any approach going into Emporia.
Is there another airport close by you could vector me into?
Horizon 2556, contact Wichita now 126.7.
126.7 Hayes and 2556.
Number 206, Victor Sierra, if you want vectors for the approach, I can get you going towards Forbes, Topeka. I can get you going towards Manhattan.
Let's go to Topeka.
All right, November 206, Victor Sierra, Roger. Stay by for 1 second. For now, just fly heading 090.
Going to 090.
Medevac 821 Tango November. Descend and maintain 10,000. The Wichita Tenor is 3053.
Descend maintain 10,000. Medevac 821 Tango November. Descend Air Street November Golf Checker 180.
November 630 with the Foxtrot radar source system ready to contact us on Tower 19.3. Number 93 November Golf KMC Center.
KMC Center, Meridian September.
All right, November 878 Bravo Tango, contact Albuquerque 127.85.
178.85, rotate.
And who needs an IFAR?
Meridian September, Victor
All right, November 26 Charlie X-ray, contact Kansas City Center on 127.72.
All right, so you get the idea there. She's in the icing, needs help, starting to get a little worried. See if we can go to the next slide here. There we go. All right, so at that point, the air traffic controller came to me and they asked for some help. They said, we need to find a VFR airport for this person. I said, well, there aren't any. All of them are MVFR. Nobody is VFR right now. The best we've got is Lawrence. They had a couple of different layers, and so they had been reporting as high as 2,600 feet earlier in the day, but you know, that deck was right there around 1,500 feet, and it was pretty consistent across the area. I also reminded the controllers, look, you get her in the clouds, she's going to get into icing, so try and keep her out of it. But she was also getting pretty close to the minimum altitudes out there for clearance or obstruction clearance, so it was really important that we try to get her clear. So they eventually handed her off to another controller, and they were coordinating with Kansas City Approach, and that's the section you're going to hear next. So go ahead, Scott, and flip it back over here.
Kansas City Center 206, Victor Sierra is with you at 3,000 feet on a heading of 040.
November 206, Victor Sierra, Kansas City Center. The force altimeter is 3055. Stay in tension.
I'm receiving vectors for the ILS approach, and I've just lost the identifier. I'm sorry, I'm having a hard time. I'm in the icing.
No worries, November 206, Victor Sierra. I believe you're on a heading to intercept the ILS runway 31 at 4. Does that sound right?
Is that Foxtrot Oscar Echo?
Affirmative.
Yes.
650, are you still in icing? Do you need to climb out of it?
I'm not. I have icing on my window, but I'm not accumulating more, and it feels best to maybe stay here.
Okay, that's fine.
Spirit Wing 1700, contact Kansas City Air Approach 124.7.
24,000 Spirit Wing, 1700 reading.
Number 6 is here. So Forbes, I'm showing the ceiling there is broken at 1,500, overcast 2,200. Lawrence Airport is about 20 to 30 miles east of that. And it's showing the cloud conditions are few at 1,600, the ceiling is 2,700. So I'm not sure if you wanted to try Lawrence, might get a better idea of the visual over there.
Can you vector me into Lawrence?
Yeah, we can set you up for the ILS 3-3 if you'd like to do that.
Okay. What's the identifier for Lawrence?
It's Kilo Lima Whiskey Charlie.
Kilo Lima Whiskey what?
Lima Whiskey Charlie.
I think Kansas City, Southwest 57634, descent level 240.
Southwest 576, Kansas City Center. Descend via the boosting on arrival, landing north of Kansas City, altimeter 3053.
And 2053, descend via the Lieutenant 1. So.
West 44 Center.
All right, so you get the flavor there as well. So she was given some options. They were trying to work out where she was going to end up going. She did eventually go to Forbes. So air traffic control did everything they could to try and help her out, to give her some options. She did land safely at Forbes. She had a half an inch of ice on her airplane. And so the controllers, you know, being who they are, they wanted to calculate how much that weighed. It was about 400 to 500 extra pounds of ice on the plane. So her aircraft was not equipped to fly in icing conditions. And again, those conditions were well forecast, so you have to kind of question whether or not that was probably a good decision or not. So let's see if I can click to the next slide here. There we go. So takeaways, get a weather briefing. All of that information would have been available, and you could have made the best choice based on that information. You know, sometimes right before the holidays, especially, that was the case in this situation. People just tend to maybe take on a little extra risk trying to get to where they're going, and they don't always make the safest decisions. So get a weather briefing, make sure you're informed, stay up to date on the changes, and know your own limitations. Know that your aircraft is not equipped to fly into icing. Maybe we should think about a different route, or maybe wait and do the flight another day. Prepare for the unexpected. She wasn't expecting to get icing and not be able to shoot the approach there at Emporia, and so she had to go somewhere she didn't intend, and that is unfortunately some of the consequences for making those kinds of decisions. But ATC is your lifeline, so even if you're flying VFR and you get into trouble, reach out to them. Don't be afraid. They're there to help you. Look at pilot reports, give pilot reports. They will help disseminate pilot reports, and also they are required to disseminate the weather that they're seeing. So they will tell you what they know, and you can use that information to help make decisions when you're up there. So from there, I'm going to turn it over to Nicole, and she's going to tell you a little bit more about where you can go to find all this information. So Nicole, take it away.
Yeah, thank you. I am going to work on sharing my screen here. Yeah, so we show a couple different icing products on aviationweather.gov that you might find useful to look at different icing products. To get to our main icing page, you would select weather up here at the top, and way at the bottom of that list we have icing. Icing is one of our three-dimensional products. So we actually have products.
Nicole, sorry to jump in. We're still not seeing your screen.
How about now?
There we go.
Excellent. I'll just point those couple things out one more time. We've got under weather at the very bottom down here, we've got icing. This is kind of what you'll see when you open icing within the graphical forecast for aviation. The page loads with the current icing air mets, SIGMETs, PIREPs, and the forecast icing product or FIP severity. FIP is the forecast icing component that produces this 3D kind of picture of what you're looking at for in-flight icing. And it's run every hour from 1 hour out to 18 hours. This is right now only over the CONUS, and again we look at about 500 feet up to up to 300,000. We also have low altitude forecasts, which get a little bit more in depth at those low levels. We're still looking at ways to add the current icing product, maybe to the observation page. The current icing product would show similar information, but at the current time, using and being modified with observations like those PIREPs and radar and satellite images as well. And that combined with the weather model would provide a more comprehensive analysis of the icing hazards over those same levels and the same region. Both the SIP and FIP output the icing severity, which is what's shown here. It's a little cluttered, so I'm going to toggle some of these layers off just so it's a little bit easier to see right now. But this is the icing severity. The severity displays the areas of expected trace, light, or moderate, or heavy icing, which are estimates kind of roughly based on the accretion rate of ice on the airplane. And the levels are determined by the time it would take for an aircraft to accrete a 1/4 inch of ice on the plane. So if you're taking a look at this right now, that's assuming like trace would take about an hour to get a 1/4 inch of ice. Light could happen in like 15 minutes to an hour, moderate in 5 to 15 minutes, and then heavy icing being in that about less than 5-minute time frame to get a 1/4 inch of ice. This legend down here at the bottom could help you identify kind of which shade of blue you're looking at. Of course, the darker the blue, the more severe the icing would be. The red that you're seeing is that SLD. I think I saw a question here before. Hopefully it was answered a little bit, but super cooled large drops, or SLD, we show with kind of a red overlay. And they're typically found at temperatures ranging from about 0 degrees Celsius to -20 Celsius. They could be found colder, like -40, but they're especially important, as Brad was talking about, if your aircraft has been at below freezing levels, giving the cooled droplets a place to stick. You can switch from severity to some of the other SIP-FIP products up here in the layer selector. We also have probabilities, which I'll show you quick here. That's kind of giving that probabilistic information in a calculated likelihood of encountering in-flight icing. It's expressed as a percentage, which is generally a complex algorithm produced by scientists at the National Center for Atmospheric Research, but it essentially indicates how likely an aircraft would be to encounter icing conditions within a specific area. And then the other option you might have seen is the freezing levels. The freezing level is displayed relative to mean sea level. And I mean, as you can see this time of year, a good portion of these northern states are below freezing at the surface. So that's showing that surface level freezing and then going up a little bit as you move down. One last thing I'll point out are the icing air mets and sigmets. Right now, we don't have a whole lot going on sigmet-wise, but we do have a couple air mets that are showing that icing level, especially in the north up there. You can filter those again off like I just did in that layer selector, or you could use the products dropdown and go to a page with only like air mets. And in this case, again, we're looking specifically for icing, so cutting some of those other products out. You could see where icing is expected, where the freezing levels are kind of taking place. It gets a little busy if you have everything toggled on, but you can pretty quickly and easily toggle layers on and off to see what you need. The air mets that you're seeing here are published by our forecasters like Scott here at the Aviation Weather Center. And then Chelsea and other CWSU folks help us out getting advisories or CWAs out over their airspaces a little more quickly, then maybe we can get our SIGMETs out. With that, I'm going to pop to the observation page and show you guys you can filter out some of these extra things if you want to filter out some of the PIREPs so that we don't have, you know, everything all at once. You can look at just a couple different things. We could filter out some of the other areas to see more kind of specific icing PIREPs up in that area. And with that, I am pretty much done showing what we have here on the website. I believe I was the last presenter, so I will open it up to questions on aviationweather.gov, or for Brad and Chelsea on icing, and Scott, maybe if you could help navigate some of the questions in the webinar, that would be great.
All right, thanks, Chelsea. Thanks, Nicole. I'll jump in here real quick and kind of wrap up the workshop. Thank you all for submitting your questions. For some of those that we didn't quite get to, we have your email address, so we'll definitely get those answered and back out to you, hopefully yet this evening or maybe tomorrow. But real quick, just wanted to share a little bit about the Weather Ready Nation. Basically, NOAA's Weather Ready Nation is an initiative that kind of prepares industry, the community for extreme weather events with the ultimate goal of saving lives and preventing economic loss. If you have an organization, whether that be a business, a school, etc., you can actually become a Weather Ready Nation ambassador. Ambassadors inspire others to be a force of nature by being ready, responsive, and resilient to the dangerous impacts of severe weather. In our case, aviation weather, it's all about training, and especially for the GA community, we love doing these outreach events to kind of help with, you know, icing fill in some of the gaps that maybe you didn't get during your pilot's exam, and maybe your CFI didn't kind of cover those in depth. So this is a perfect opportunity for us to host these webinars and kind of share that information. Basically, it just looks to strengthen partnerships between the NWS and the aviation community. If you want to learn a little bit more about becoming a Weather Ready Nation ambassador, just click to that link, weather.gov/WRN, for more information. Sorry about that. Looks like I lost audio, but just real quick, acknowledgments, thank yous, contact information, and then social media links for everything aviationweather.gov. Feel free to email anyone at those email addresses, and we'll get you a response as soon as we can. And with that, thank you all again for attending, and we'll go ahead and close out the webinar. Have a good evening and safe flying during the holiday.